If you could point a telescope at the sky and see a galaxy just turning on for the first time, what would you expect it to look like? Something dim, something messy, mostly hydrogen and helium. A weak little smudge that barely survived the chaos of the early universe. But on January 28th, 2026, NASA and ESA released a Webb result that doesn't match that mental picture at all. A galaxy called MOM-Z14, confirmed at a redshift of 14.44, meaning we're seeing it as it existed around 280 million years after the Big Bang. That's not ancient in the usual sense. That's basically the universe still learning how to be a universe. According to the NASA Webb team, MOM-Z14's light has been traveling for about 13.5 billion years to reach us. And here's the hook. MOM-Z14 doesn't look like a shy newborn. It looks bright, compact, and this is the part that matters most, chemically ahead of schedule. The team reports spectral features pointing to nitrogen enrichment, and in the technical analysis, an abundance pattern that hints at unusual early stellar populations. MOM-Z14 isn't just the farthest. It's a chemistry story about what the first massive stars may have been doing. Fast. So in this video, we're going to do 4 things in order. First, what Redshift 14.44 actually means, and why it's so hard to confirm. Second, how Webb verified MOM-Z14, what the spectrum says, not just the headline. Third, why a bright, tiny galaxy with nitrogen this early is so provocative, without drifting into breaks physics nonsense. And fourth, what astronomers will try next. Because this isn't the end of the story. It's the beginning of a very specific new test of the first stars. Let's start with the number that made MOM-Z14 famous. Z equals 14.44. Redshift is one of those words people hear 1,000 times and still picture wrong. A common mistake is thinking of redshift like an object moving away through space, the way a car drives away from you. But at cosmological distances, what matters is that space itself expands. The light stretches as it travels. So when NASA says MOM-Z14 has a redshift of 14.44, they're saying the universe has expanded by a factor of 1 plus Z, which is 15.44, while that light was on its way here. In other words, those photons left MOM-Z14 with wavelengths in the ultraviolet. And by the time they reached Webb, the expansion of space had shifted them into the infrared, right where Webb is strongest. And that brings us to the phrase cosmic dawn. Cosmic dawn is roughly the era when the first generations of stars and galaxies switch on and begin transforming the universe, especially by producing high-energy light that starts changing the state of hydrogen gas everywhere. NASA's January 2026 release frames MOM-Z14 as another step deeper into that period, pushing closer to the time when the first luminous structures formed. Now, you'll notice something. We keep saying around 280 million years after the Big Bang, and the title you clicked might say 285, and you'll see other numbers floating around for similar objects. That isn't because anyone is being sloppy. It's because converting redshift into years after the Big Bang depends on the cosmological model parameters you assume. NASA's release uses a value of about 280 million years for MOM-Z14, which is the number we'll treat as the reference. But none of this matters if the redshift isn't real. And that's the key point. Webb doesn't win by finding a red dot. Webb wins by confirming. In the early days of Webb, there were many high redshift candidates identified by their colors, objects that drop out in certain filters because neutral hydrogen blocks light blueward of a particular wavelength. That's the famous Lyman break idea. Hydrogen absorbs photons with energies above the Lyman limit, so you see a sharp change in brightness across wavelengths. Photometric redshifts estimated from colors, are incredibly useful. But they're also vulnerable to imposters. Dusty galaxies, certain kinds of emission line galaxies at lower redshift, or even blends of objects that trick the filters. The real gold standard is spectroscopy. Spread the light out into a spectrum and measure the features directly. For MOM-Z14, NASA and STSCI both emphasize that Webb used NIRSpec, Webb's near-infrared spectrograph, to confirm the galaxy's redshift. And in the team's technical report, they describe how that confirmation happens in practice. A sharp break consistent with the Lyman alpha region, plus multiple detections of rest ultraviolet emission lines at consistent wavelengths, together locking the redshift to Z-spec equals 14.44 with tight uncertainties. That's what makes this a distance record in the meaningful way. It's spectroscopically confirmed, not just the reddest smudge. Now let's put that number in context. Before MOM-Z14, and Webb's famous early universe record holders included objects like JD's GSZ140, confirmed at a redshift around 14.3, corresponding to just under 300 million years after the Big Bang in NASA's description of that result. MOM-Z14 edges beyond that, not by a billion years, not even by 50 million years. It's a smaller step in time, but it's a huge step in difficulty. Because as you push to higher redshift, you're fighting three enemies at once. First, the light is stretched farther into the infrared, so you need the right instruments. Second, the objects are intrinsically young and small, so there's less time to build stars. Third, the intergalactic medium becomes more neutral as you go back, making certain features harder to see cleanly. And yet, MOM-Z14 shows up as a bright point in Webb's data. NASA's release explicitly calls it a bright galaxy at this distance. So the obvious question is, how can something that early be bright enough to stand out? One answer would be gravitational lensing, cosmic magnification. And Webb does frequently use lensing fields to see faint objects. But the MOM-Z14 story, as described in the team's technical analysis, is even weirder. They describe it as extremely compact, with a measured effective radius on the order of tens of parsecs, about 74 parsecs in their fit, yet still resolved enough that they argue an active galactic nucleus is unlikely to be dominating the light. Let's translate 74 parsecs into something you can feel. 1 parsec is about 3.26 light-years. So 74 parsecs is roughly 240 light-years across, in that characteristic radius sense. Tiny compared to a galaxy like the Milky Way, which spans on the order of 100,000 light-years. So you have a galaxy that is, in physical terms, almost like a dense cosmic seed, yet bright enough to be detected and confirmed at the edge of Webb's reach. This is where the story stops being distance bragging and becomes astrophysics. Because brightness implies stars, and stars imply that gas has already collapsed, formed massive stars, and enriched the surrounding medium with heavier elements. And that brings us to the unique angle of MOM-Z14, nitrogen. When astronomers say metals, they mean everything heavier than hydrogen and helium. In the early universe, the very first stars, population 3 stars in the classic picture, form from pristine gas, no metals at all. Then those first stars live fast, die young, and pollute their surroundings with new elements forged in their cores and in supernova explosions. So seeing heavy element signatures at high redshift isn't shocking by itself. Webb has been finding evidence of early chemical enrichment since its first deep surveys. What's striking is which element stands out and what that might imply about the kinds of stars that formed. In the MOM-Z14 technical report, the team highlights nitrogen emission and discusses a high nitrogen-to-carbon ratio, even describing it as highly supersolar. In that specific relative sense, an abundance pattern they compare to what's seen in local globular clusters and among ancient stars in the Milky Way. That's a very specific claim with a very specific implication. It suggests that inside this tiny early galaxy, the star formation may have occurred in dense clusters, producing unusual stellar populations, possibly including extremely massive stars, capable of enriching nitrogen rapidly relative to carbon under certain conditions. Now, to be clear, this is where we have to be careful. The spectrum gives you line strengths. Interpreting those line strengths as abundances depends on models of stellar populations, ionization, and gas conditions. The team is making an argument based on the best available modeling, but they're also describing a scenario that needs follow-up. So we're going to treat it the right way, as evidence pointing to a possibility, not a final verdict about what exact kinds of stars live there. But even as evidence, it's fascinating, because nitrogen is not the easiest element to get early in large quantities, depending on which production channels dominate. And this is where the cosmic dawn part becomes real. We're not just asking, is there a galaxy? We're asking, what kind of stellar physics turned on first? To understand why nitrogen is such a loaded clue, we need to talk about timescales. At 280 million years after the Big Bang, you can absolutely have multiple generations of massive stars. Massive stars can live for only a few million years before exploding, enriching gas quickly. So enrichment itself is not impossible. The tension is about how much, how fast, and in what pattern inside a galaxy that also appears compact and actively forming stars. In the MOM-Z14 analysis, the team describes indicators of a rapidly rising star formation history, and including a ratio comparing very recent star formation to longer timescale star formation that suggests a sharp increase over just a few million years. So imagine the scene: a tiny region, a couple hundred light years across, very blue ultraviolet slope, suggesting little dust and a young population in their fit. Bright enough to register at redshift 14.44, and chemical fingerprints that look mature in a particular way. That combination is what makes MOM-Z14 feel like a challenge. Not physics is broken, more like our simpler stories about early galaxy growth may be missing key pathways, especially pathways that build dense, efficient star formation quickly. Now we should ask the obvious skeptic question: could this be a black hole? An active galactic nucleus can make a compact object look extremely bright. And at high redshift, that's always on the table. But in the technical report, the team argues that the object is resolved and that the properties are inconsistent with an AGN dominating the light, though they frame it as suggesting rather than absolutely ruling it out. That's exactly the right language for this stage. A GN contribution is a hypothesis to test, not a monster to fear. So if not a black hole beacon, then we're back to stars. Which brings us to the question that matters. What does MOM-Z14 imply about the first massive stars? Here's one clean way to think about it. If you see a high nitrogen to carbon ratio at this epoch, one possibility is that the enrichment came from a stellar population with yields that favor nitrogen production under certain conditions, like very massive stars, rapidly rotating stars, or stars forming in environments that push nucleosynthesis down unusual channels. The MOMZ14 team explicitly connects the abundance pattern they infer to patterns seen in globular clusters and ancient Milky Way stars, suggesting a link between early dense cluster star formation and chemical signatures that survive into the present day. That is an astonishing idea if it holds up, because it would mean Webb isn't just spotting a random early galaxy. It's possibly watching a mode of star formation that echoes forward across 13.5 billion years of cosmic history. A kind of chemical accent that appears in our own galaxy's oldest relics, being spoken in real time at cosmic dawn. Now let's zoom out a bit, because MOM-Z14 is part of a broader Webb pattern. NASA's January 2026 release doesn't present MOM-Z14 as a lonely freak, and it places it in a growing list of bright early galaxies that are defying expectations and demanding new theories about the early universe. And the MOM-Z14 technical paper quantifies that tension sharply. The authors argue that the implied number density of bright galaxies at these redshifts is far higher than pre-JWST consensus models, even quoting factors greater than 100 in that comparison. This is one of those moments where you can feel the field recalibrating. Before Webb, galaxy formation models were tuned to match the best data available, primarily from Hubble and other instruments that couldn't easily reach the same infrared depths. Webb changed the observational game, so there are two broad possibilities, which one neither requires melodrama. Possibility 1. The early universe really did produce bright galaxies more efficiently than we expected, perhaps because star formation was burstier, clumpier, and less dust-enshrouded than assumed in some models. Possibility 2. We're still learning how to interpret Webb's selection effects, lensing biases, and the ways emission lines can boost brightness in certain filters, meaning the population might look more extreme in photometry than it is intrinsically. MOM-Z14 is powerful because it is not only photometric, it is spectroscopic, so it becomes an anchor point. One confirmed object that forces models to at least allow the existence of something like this. Okay, so how does the confirmation actually work in a way you can visualize? Imagine you're looking at a rainbow, but the rainbow is in infrared, and instead of smooth colors, it has fingerprints. Lines where atoms in the galaxy's gas emit light at specific energies. At very high redshift, those ultraviolet fingerprints are shifted into near-infrared wavelengths Webb can measure. If you detect a set of lines that all correspond to one redshift, meaning they're all shifted by the same factor, you can lock down the galaxy's distance. In the MOM-Z14 report, they describe a sharp break plus multiple rest UV emission lines detected at about a few sigma level, together building the case for Z equals 14.44. So the mental picture is a spectrum that's quiet, then suddenly drops because hydrogen absorption bites out the flux. Then, scattered on top of that spectrum, a handful of peaks, emission lines, each one a little lighthouse telling you, I'm here, I'm real, and I'm at the same redshift as the others. That is the difference between a candidate and a confirmed record. Now we're ready for the real question. Why would a galaxy this early be both compact and chemically interesting? There's a clue in how the MOM-Z14 authors describe the object's size and star formation. A very compact region can mean a very high density of gas. High density can mean star formation that turns on fast, especially if the gas cools efficiently and collapses into clusters. And once you form clusters of massive stars, chemical enrichment can happen quickly, because massive stars return material to the surrounding medium on very short timescales. So it's not that chemistry can't happen in 280 million years, it's that the details of the chemistry and the brightness suggest an environment that is intense. And a cosmic pressure cooker. And the nitrogen hint, if it holds up under follow-up, points to an enrichment pathway that might not be dominated by the same normal stellar population assumptions we use when modeling later galaxies. Let's also deal with one subtle point, the word mature. You'll see headlines saying early galaxies are too mature. That's a sloppy phrase because maturity can mean morphology, mass, metals, dust, or star formation history, and these don't always move together. In MOM-Z14, what's striking is not that it looks like a modern spiral galaxy. It doesn't. What's striking is that it appears luminous and chemically structured in a way that suggests very rapid early processing, especially if the high nitrogen relative to carbon is confirmed robustly. So instead of mature, the better word is efficient. MOM-Z14 suggests the early universe could assemble luminous, chemically distinctive star-forming regions very quickly, at least in some places. Now let's talk about what happens next, because this is where good science beats good headlines. The January 2026 NASA and STSCI releases frame MOM-Z14 as part of Webb's expanding frontier, and they emphasize that these bright early galaxies are demanding new theories and more observation. So what observations would actually test the chemistry story? There are three major follow-ups that would move MOM-Z14 from provocative to diagnostic. First, deeper, higher signal-to-noise spectroscopy. If you can detect more lines with higher confidence, you can constrain physical conditions, electron temperature, ionization parameters, and more robust abundance estimates. Second, spatial information. And if Webb can resolve the light enough to see whether the emission is concentrated in one knot or spread across multiple regions, that changes how we interpret compactness, and whether there might be multiple star clusters or a central engine contributing. Third, search for companions and environment. A galaxy at Z equals 14.44 doesn't exist in isolation in theory. It lives in a developing cosmic web. If it sits in an overdense region, an early node of structure that could help explain rapid formation. All of these are the kinds of questions Webb is built to push on, especially when you have a confirmed extreme object worth spending time on. And this is where we should be honest about uncertainty. MOM-Z14 is real in the sense that its redshift is confirmed in the way astronomers mean confirmed. But turning a spectrum into a story about the first massive stars involves modeling steps. Those steps can improve, and they can change. The responsible way to think about MOM-Z14 is: the universe has shown us a bright, compact galaxy at 280 million years. The spectrum suggests an unusual chemical signature involving nitrogen. The most exciting interpretations point toward dense clusters and unusual, massive stars. And the next observations will decide how much of that interpretation survives. That's not hedging. That's science doing its job. Now, there's one last layer to this story that's easy to miss. At these redshifts, we are approaching the era where the first stars, true first stars, should begin to appear. The very earliest stellar populations are expected to form out of almost pristine gas. So when you see a galaxy with evidence of chemical processing, you can ask a breathtaking question. Are we catching the universe right after the first stars have already lived and died, meaning we're seeing the second wave? Or are we seeing a region where star formation began so early and proceeded so intensely that by 280 million years, it has already left chemical fingerprints that resemble patterns we still see in relic populations today? The MOM-Z14 paper leans into that second possibility by drawing connections to globular cluster abundance patterns and ancient Milky Way stars. If that link holds, it would mean Webb is not just doing archaeology, it's doing genealogy, and tracing a line from the first dense star-forming clusters to the chemical signatures embedded in the oldest stars near us, connecting two extremes of cosmic time with the same elemental fingerprints. And if that sounds dramatic, good, because it is dramatic. Not in a laws of physics are shattered way, in a we can now test ideas that used to be pure theory way. For decades, the first stars were almost entirely a simulation problem, a modeling problem, a philosophical problem. Now Webb is handing us spectra from the epoch when those stars should exist and saying, here, argue with the data. So yes, MOM-Z14 is the farthest confirmed galaxy we've ever seen, and that record matters. But the real story is that MOM-Z14 is a bright, compact, and chemically intriguing object sitting almost unbelievably close to the beginning, 280 million years after the Big Bang, forcing us to ask what kinds of stars turned on first, how quickly they enriched their environment, and whether the earliest clusters in the universe left fingerprints that still echo in the Milky Way today. And that's why this discovery is worth your attention. Because Webb isn't just extending a distance record, it's turning cosmic dawn from a blurry myth into a laboratory, one spectrum at a time,